Hello everyone, welcome to the machine learning class. In this video we will be exploring the ensemble models. Basically, as it can be understood from its name, we're going to be ensembling the models, or in other words, we are going to be combining the outcome of the single models. Let's make an analogy before getting started. In the machine learning field, we have models that enables us to predict the outcome, right? We sometimes use decision trees, which are known as CRTs, classification and regression trees. Sometimes use support vector machines, sometimes artificial neural networks, sometimes logistic regression, depending on the data set, depending on the problem, and so on and so forth. And the most important thing is, depending on our experience, we'll go ahead and pick our model and then make trial and error. Whichever does the best, then we'll continue with that one, right? That's the simple idea behind these process, right? In the ensemble model, what we think, okay, why are we using only a single model? Why cannot we combine these two or three just to make a better outcome? Because let us assume that you are managing a marketing company, right? And what you think is you've got these three great people and their decisions are usually valuable. Let's say you're discussing about a future marketing strategy, and you know that all these three people are great, but they might have different opinions on the next project, right? Even though you know that they are the expert, they know the things very well, sometimes their ideas will differ. If, let's say, there is a project that you are intending to invest on, but then, you just don't want to go with your idea, with your own idea. Instead, you want to take the ideas from these three people who are known to be expert in the field. Okay? So, two out of these three people said yes, we should invest on the future project, and one out of these three say no, we should not because it's not worth to do it, or it's very risky, and so on and so forth. What would you do as the manager? You would simply go, I mean, if you think that these people have the equal, weight of expertise in the field, what you intuitively do is take the voting, right? Make a voting. So two out of these three people, if there are two out of these three people are saying yes, we should invest, you most of the time go ahead and make an investment because two out of three is greater than one out of three, right? Or let's say there is a project that you are intending to invest, but you don't know how much you will be investing. So it's a continuous outcome problem now. So now one of these three people says we should invest 100,000. The second one says that we should invest 200,000, and the third person says that we should invest $300,000 on this project. So what would you do again if you again believe that these people have the same, equal level of expertise in the field? You would take the average. Just like that, in the machine learning models, instead of going with CRT only, what you think is on the same problem, okay, you take the idea from the SVM and the ANN as well. And then if it is a classification problem, or in other words, it's a 0-1 problem, you make the voting. If it's a continuous outcome prediction, then again, you make the averaging. All right, that's how simple it is. And ensemble models are, again, very simple to study and very intuitive to study. So even, at this level, in the introduction level, we can go ahead and create our own ensembling model, that's what I have seen, in my experience. All right, let's go ahead and get started reading the slides. Second slide is, okay, we are using multiple models to improve the performance. That is what the intention is, right? Our goal is to improve the performance. So whatever enables us to improve performance, we will follow that pathway. Okay, and we would like to combine multiple hypotheses. That means, multiple decisions to build a better decision or better hypothesis. So we want to improve the results through averaging if we have the continuous outcome. Remember that, how much we will be investing. Or voting, when we have the binary outcome. Remember whether we should invest or not, 0 or 1 problem. Sometimes it may be too difficult to build a single model that works well. Therefore, ensembling model is a very good alternative to those single models. And basically what we're doing is we're aggregating the multiple weak learners to produce a strong learner. Remember, it's a machine learning, so our models learn from the previous experience, therefore we can call them simply learner. So in the single model case, that might be a weak learner. That means it might not be as strong as an alternative ensemble model, ensemble learner. Therefore, what we want to do is we want to combine these weak learners to create a strong learner. That's what the idea is. And this is the simple picture of it. We have n models and we're combining them and we're making a final model. Again, as we have discussed earlier, it could be a continuous outcome that we will have to average the things, or it could be a classification outcome that we are usually taking the votes, the voting based outcome. That's what we make the decision. All right, let's just recall the example that we have given in our CRT lecture, categorization and regression tree. Remember, we had these 14 days from day 1 to day 14. We have the weather, humidity, wind, and at the end of the day, by using these 3 independent variables, we want to go ahead and predict whether Ali will be playing tennis or not on a given day. Okay, and these are the actual outcomes. There are 14 days, and these 14 days will be used to train our machine learning model, or in other words, learner. Once we've learned out of this, we can go ahead and test ourselves on the 15th, right? And this was the rule that we have learned from our CRT model. So if the weather is sunny, then the only thing that we should look from now on is the humidity variable. So in other words, if the weather is sunny, then the wind variable is not important at all. I don't even look at it. I directly go ahead and look at the humidity, and if the weather is sunny and the humidity is normal, then I will say that Ali will go ahead and play, as you can see. Yes, right? Or if the weather is rainy and the wind is, then if the weather is rainy, the only value, the only variable that I, consider is the wind variable now. I don't even look at the humidity. That's what I've learned from the training data. Okay? So if the weather is rainy and the wind is weak, then I do and go play, right? I go ahead and play. If the weather is rainy and the wind is strong, I don't play the tennis. Okay, that's what we've learned by using the CRT model. These are our basically if and then based rules. Okay, so what we're doing here is that, okay, now for the same data, for 14 days, everything is the same. So this is our training data, and the 15 days is our test data. Okay, we will learn out of this 14 days, and we will test ourselves on the 15th day whether Ali will be playing tennis or not. Okay, but what we're doing here is that, okay, now let's just go to the second example. I mean, the next slide, right? Let me use my pen here. Okay, so basically based on our CRT model, okay, CRT model, the decision is, okay, let's go back and come back. So the decision is, if the weather is sunny and the humidity is normal and the wind is strong, right? I'll go ahead and apply my rule. Weather is sunny and the humidity is normal, and then wind, I don't even take a look at it. I don't even consider it because it doesn't play any role in my decision for this specific case. Therefore, okay, now it seems that I'm going to go ahead and play tennis, right? Weather is sunny and the humidity is normal, and then I'll go ahead and play the tennis, right? So my answer will be yes. So if I look at the decision tree, okay, basically, let's say the answer, or you would say maybe classification, whatsoever you name it, okay? The class variable, the prediction that you make is yes, okay, right? That was the outcome that you got from the CRT, categorization and regression tree. Let's say in the future, you've used the same 14 days, okay? The same exact 14 days as the training data, and then now you learn something out of it based on A and N, but this time your rules are different, everything is different. It's not CRT anymore. So maybe for the same exact case, but the weather is sunny and the humidity is normal and the wind is strong, maybe ANN's decision will be something else. Maybe ANN will think that, okay, it is no. I mean, sorry. I guess I'm messing up here. Okay, I fix it now. All right. This is sometimes hard to use. All right. Okay, maybe ANN will think that no, it's not going to rain. Let us assume that you've done the same exact thing, same exact 14 days for training for the SVM model now, sport vector emissions. And she also thinks that Ali will play tennis, right? So CRT thinks that Ali will play tennis, ANN thinks that Ali will not play tennis, and SVM thinks that Ali will play tennis. So based on voting, what you will do is, whatever the majority vote out of these three, which is 2 yeses and 1 no's, therefore your ensembling is, okay, your overall ensembling outcome will be, your answer will be yes, since there are majority of the decisions are yes here. Okay, that's how simple it is. All right, so if, let's say, if this was a continuous outcome problem, instead of, yes or no, if we were, let's say, trying to figure out the probability of me playing tennis, okay, so CRT, ANN, again, same exact example, and then SVM, okay. So now the prediction, was continuous this time, okay. So we're trying to predict the probability, not it will be, Ali will be playing tennis or not, but I'm gonna, I'm trying to calculate the probability of me playing tennis. Okay, let us assume that CRT thinks that Ali will play tennis with the chance of 0.6, and ANN thinks that Ali will not play tennis with the chance of 0.4, and SVM thinks that Ali will play tennis with the chance of 0.8. Okay. Basically, if it's above 0.5, then CRT thinks that Ali will play tennis. Since this is below 0.5, right, the 0.4, therefore ANN thinks that he will not play tennis. Okay, so what we'll do this time is there's no yes or no's, but we have continuous outcomes, and if they have the same, level of expertise in our, in our consideration, well, we will think that, okay, let's take the average, 0.6, 0.4 plus 0.8, it's 1.8 in total, divided by 3, it's going to give us 0.6. That means, since it is above 0.5, basically, I mean, yes, from the continuous outcome perspective, the ensemble model will say that, okay, the probability of Ali playing tennis will be 0.6, okay, which means, yes, Ali will be playing tennis just because it's above 0.5 level. All right, that's how simple it is, and everything will be, aligned with this idea, with this thinking. Okay, so this is a, weather forecasting example, whether it will be, cloudy or sunny. So that's, either 0 or 1 problem, right? This is 0, this is 1, and then this is 1 again, sunny, and then 0, 0, 0, 0, and 1, 1. Now the idea is we have the models, 5 models. Instead of 3, I have 5 of them now. The first one thinks that, okay, let this first day be Monday, and then second Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, okay? My first model thinks that when I make a forecasting for the next week, my first model thinks that, okay, it's not going to be sunny Monday. The Tuesday will not be sunny either. And then Wednesday will be sunny, and the Thursday will be sunny, and so on and so forth. So every single model in my, model box, let this one be SVM, and this one be CRT, this one be logistic regression, this one be ANN, and let's say this one be random forests, okay, or something else, whatever you think of. All right, so we've got 5 of those, and first model thinks that it will not be raining, and then for the first day, for this Monday, let's say, okay, let's take a look at Monday, okay. For Monday, my SVM thinks that it will not be raining. Second model, CRT, thinks that it will be sunny, right? The third one will be cloudy. ANN thinks, again, it's cloudy. Random forest thinks that it's cloudy. So when I look at 5 of my models, okay, there are 5 models, 4 of these 5 thinks that it will be cloudy, not sunny. Therefore, I will go with the voting 4 out of 5 says cloudy. Therefore, my ensemble decision will be cloudy. All right, and if we apply the same thinking here, we've got 3 sunny here and 2 cloudy. Therefore, my decision will be sunny. Here will be sunny. Here will be cloudy, cloudy, cloudy. Sorry, sunny and sunny. So when we look at the model, let's say if we were to work with only SVM model, if we did not consider CRT and LR and ANN and RF, okay? So assume that we're only going with SVM. So when you look at the SVM and the reality, the actual situation, the observed outcome, that's what I mean by here, okay? So when you look at it, SVM is making misclassification on Tuesday, Thursday, and Sunday. Of these 7 predictions, 3 of them were wrong. When we apply the same thing for SCRT, again, CRT is making 3 mistakes out of 7 days when it's compared to the reality. That means observed outcome. And logistic regression is making 3 mistakes. ANN is making 2 mistakes. RF is making 2 mistakes. But when we apply the ensembling idea, okay, of these 5 based on voting, and this is our combination or ensemble, right? So when we look at the outcome and compare it with the reality, okay, so basically I'm not making any mistake. Cloudy, cloudy. Tuesday was sunny and my expectation was sunny. Again, sunny. Wednesday, sunny. Wednesday, sunny. Cloudy, 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 cloudy. Saturday, sunny. And in my expectation, again, it's sunny. And then sunny, sunny. So when I look at the ensembling case, I'm getting the maximum accuracy out of it. All right. That's what the, again, simple wording approach. So the motivation behind it. No algorithm is best. No algorithm is best for all circumstances. So one algorithm will be doing well for a certain data set, certain conditions, and then one algorithm does do well, better in the second data set, and so on and so forth. So our thing is we always make trial and error by using these models on the data sets. Okay? And then, so therefore, if we combine multiple independent decisions, basically it will enable errors to cancel each other out, just like the previous slide that we have seen here. Okay, so if you use multiple learners, we're hoping to decrease our error rate. That's what it means. And correct decisions are amplified. So therefore incorrect decisions will be muted. That's our expectations from the from the ensembling models. Okay, now types of ensemble learning. One type is different algorithms, different learning algorithms. That means, okay, for the same training data set, you are using CRT, SVM, and artificial neural network. So these are three totally different learning algorithms. The way that they work are different. Okay, so different algorithms. So basically, in the previous example, that's what we have done. We have applied different algorithms to make an ensembling. Okay, so this is the first type of learning, ensemble learning. Second thing is algorithms with different choice of parameters. Now, what I think that, okay, I don't want to compare, or I don't want to use SRT, SVM, and ANN, but what I want to do is I want to create 3 different CRT models, categorization and regression tree models. 3 different ones though. As you may recall, in the Rattle environment, Rattle allows you to play with the parameters. Okay, so like maximum depth is one of those parameters, minimum bucket size, things like that. Okay, minimum ciplet, right? These are 3 of those like 5 or 6 parameters that you can change in the Rattle environment. So what I want to do is, okay, I want to create a CRT model with different parameters. Let's say I'm going to make maximum depth 3 and minimum bucket size, let's say 10, and minimum ciplet is, let's say, 25. Okay, now I'm using the same CRT model but with different parameters. Now I want my maximum depth to be 5 instead of 3. Minimum bucket size, I want to do it 25 instead of 20 or 10, and minimum ciplet, I want to make it 30 now. Okay, so things like that. So I am actually creating 3 different CRTs. The way that they work is the same, But in the details, since the parameters are different, the outcome that we will be getting will be different. It's like you have three same people, right? But their training way is different. So let's say you have three same people that you work with, okay? They are the same exact people, but one of them is trained with different skill sets, okay? And the second one is again trained with different skill sets. Third one is the same. So if you train the same people with different skill sets or with different, education and so on and so forth, you name it, and if you ask them a question on a certain subject, their answers will be different, even though they are the same. They were the same people, but now they are different people with the different training. Therefore, their decision on the same question will differ. So what we want to do is, okay, we want to combine these three different outcomes again. And again, same thing can be applied to here easily. I mean, instead of this will be SVM, CRT, LR, ANN, and RF, what I want to do is, okay, CRT1, CRT2, CRT3, or LR1, LR2, LR3, LR4, LR5. Okay, so basically I am creating the same algorithm, same, model with different parameters. That means I am changing their nature. All right? Okay, but again, from classification perspective, from continuous outcome perspective, they are they are the same. Okay, we do voting if we have classification, we average them if we have continuous outcome. Okay, so the third thing is different sets with different features. Okay, which I'm going to lecture in my one of my other videos. I'm going to dedicate a class for these. Okay, different features and different subsets because they have their own names. It's called bagging, boosting, bootstrapping, things like that. I'm going to be dedicating a totally video on it. So basically, when we use different features or different variables or different subsets, meaning different samples, okay, we will name them. Their names will the way that we follow the model, the pathway that we will be building is called something different. Like they are going to be called bagging, boosting, random forests, and so on and so forth. Okay, but I'm not going to talk about any details at this level. But for your information, there are 4 types of building ensemble learning. 1, different learning algorithms. 2, different choice of parameters with the same algorithm. 3, for the same data set, you don't want to use every feature, every single variable. You want to use maybe 2 out of these 3 variables, but you are randomly choosing them. Okay, so or the 4th is different subsets. That means you don't want to use all of these 14 days. Remember, there are 14 days in my training data set, right? Maybe you want to use 10 of them only. Okay, and there are reasons behind it. That's why we are doing it. But again, you randomly do it. All right. So this is the basic understanding from different types of ensemble learning. Basically, you have the same. The first one is different algorithms. Okay, different algorithms. Same set of training data. That means same data. Okay, algorithms 1, and then algorithm 1 has an answer, or classification, right? Algorithm 2 has a class. Algorithm N has a class. And therefore, at the end of the day, we either vote, ensemble based on voting, or averaging. That's it. Okay. And the second thing is that we have different parameters: parameter 1, parameter 2, parameter 3, parameter N, right? And then again, we have different answers, even with the same training data. Again, we do our ensembling with either voting or averaging. Okay. The very last slide, okay, of it is different algorithms or parameters. Okay, doesn't matter at this point, but same set of training data again. I mean, everything is the same until this point, but different weights. What does that mean? Different weights. Okay, let's say we are using ANN again, or decision tree in this example, right? Yes, no, yes, or continuous outcome 0.6, 0.4, 0.8, whatsoever. What we want to do is, okay, now we think that I have 3 guys here, right? 3 people that helps me to make my decisions. In this specific example, as you may remember, we thought that they have the equal level of understanding. So the quality is the same. Okay, so I trust these people on the same level. I rely on them on the same level. Okay, so what we want to do is, let me just copy this slide and paste it here. All right. So what we want to do here now is, okay, we think that one of these people in my team, let it be CRT, we think that, his decisions or her decisions are most of the time correct. Okay, therefore I think that I want to give this guy 2 times more weight than, the others. Okay, so if I'm going to make a decision, the 50% of the decision, because if, let's say, these are like, 2x and x, 1x and 1x, right? So that means, okay, if I've got a piece of cake, if I've got a cake that I'm going to share these three guys, that means 50% of the people, 50% of the cake will go for the CRT. 25% of the entire cake will go for the ANN, and then 25% of the cake will go to the SVM, right? That means CRT, to me, in my ensembling decision, will be 2 times more important than, or more weighted than the others. Because in the past, I've seen this guy and then this guy always makes correct decision, whereas ANN and SVM, I've seen that, they do well, but they do not do as well as the CRT does, okay? Therefore, I have assigned some weights, all right? I have assigned some weights, all right? So basically what reflects to me is that, okay, now previously I was doing simple voting. Yes, no, yes. Out of these three, 2 of them are yes, therefore I'll go with yes. Here, it doesn't work the same way, okay? So basically what I will do is I'll take a weighted average. That means, okay, let me just go ahead and make, instead of yes, let me use a number, which is 1, okay? And for no, let me use 0, and for yes, again, let me use 1, just in order to quantify this, okay? Otherwise, I don't have any other intention behind it. 1, 0, and 1. So what we will do is, we'll just multiply. That's what's called weighted average, right? In statistics and mathematics, right? I'm going to go ahead and multiply this 50% by 1, and then 25% by 0, and then 25% by 1 again, okay? So basically, 0.5 times 1 plus 0.25 times 0 plus 0.25 times 1. Okay, therefore, 0.5 comes from here, and then 0 comes from the second, and then 0.25 comes from the third unit, and then therefore in total, my idea is 0.75. What that means is that, okay, since it's closer to 1, right? Remember I labeled yes as 1 and no as 0, therefore it's above 0.5. If it's above 0.5, that means it's close to 1. That means my decision will be yes, regardless. Okay, but again, the way that I had done in the past is different. It was simple voting, right? 2 out of 3. Now I'm taking the weighted average. Same thing here. Let's say if I were to have the same numbers here, okay, 50% and 0.6, 25% and 0.4, and then 25% and 0.8. So basically, if you were to calculate the probability of me playing tennis, you'll go ahead and multiply 50% times 0.6, 25% times 0.4, and 25% times 0.8. We can go ahead and do it. So here, 0.5 times 0.6, the first will be what? 0.3. Plus 0.25 times 0.4, it will be 0.1. Okay. And 0.25 times 0.8, it will bring us 0.2. All right, that means 0.3 plus 0.1 plus 0.2, it's going to be 0.6. All right, so on average, as you can see, average did not change here, but it's a luck, okay? It's a coincidence. It differs. So long story short, we were doing a basic voting or basic averaging. Now, if we think that one of the models is more important than the other two, then I assign different weights, and then I take the weighted average. That's how I've done it. If it's the classification, I will make my multiplication, and if it's above 0.5, then it will be yes. If it was below 0.5, it would be no. Okay, and then for the continuous, again, I'll just do the follow the same strategy, and then I'll get my number, which is 0.6. Okay, let's go to Excel application for this, just to make the examples clear, because it's it's a very important subject in machine learning area, ensemble learning. Okay, so the first example is again, whatever we had done in the PowerPoint file, we'll do it for the Excel file. Okay, so here we're going to make our decision. If we, these are the single models, CRT, ANN, and SVM, and the reason that I'm going with 3 models only, in the voting, if you have 4 models, if 2 of them says yes, if 2 of them says no, then you will not be ending, with a decision. Therefore, that's why I'm using some odd numbers. Okay, CRT, ANN, and SVM. CNN thinks that I will go ahead and play tennis. ANN says no, SVM says yes. Therefore, whatever is the majority. Okay, so my answer will be yes then. Okay, this is the ensemble decision based on the voting. Here, again, I have the continuous outcome now. I'm not yes, no, yes, but my numbers are 0.6, 0.4, and 0.5. Therefore, I'm going to go ahead and take the average. All right. And remember, these decisions will be made by REDL. Okay, REDL has the capability that it will give you whatever the models think, right? You can basically make an output from REDL that will give you either the classes or the probabilities, model by model. Once you have obtained those, you can go ahead and apply your own, weighting method or whatsoever you want to apply. Okay, here we're doing a basic averaging, and that's how it is. All right, different parameters. Okay, now again, the same will reign or not. So the chances, the first model is CRT1. That means, okay, I'm using a CRT model, but in my parameters, I'm going to make my minimum split as 20. What that means is that in order for the tree to make a split from that node on, downwards, you have to have at least 20 samples in it. Okay, otherwise you cannot make a splitting. All right, that's what it means. All right, so in my second model, I'm using the same CRT but with different understanding, with different analogy, different parameters. So now I want to make my minimum split 30, here minimum split 40. So all of these, even though they seem to be the same model, which is CRT, but they are different. We made them different. So the idea from the first is yes. The decision from the first is yes, and the second is no, and the third is yes. And if you make a simple voting, our idea will be yes. Here, the same thing. Again, 20, 30, 40, they are different. We're making simple averaging. All right. Whatever we had done in our PowerPoint file. All right. Okay. So the third thing is different weights of the models. Okay, we think that CRT is 2 times more important than the others, like 0.5, 0.225, 0.225. Previously, it was basically 0.333, 0.333, and 0.333, right? So, but we didn't even, multiply those things with those numbers, because basically we make the average. When you make an average, you don't even need to, if they have the equal weights, you don't need to multiply those numbers. Okay, but here, since the weights are different, then we have to apply the formula. That means weight times the number, plus weight times the number, and whatever the number that you're getting at the end of the day will be your number. So that means, okay, the first model is what? 0.5 times, yes, as you may remember, we can label it as 1, right? Instead of yes, we're using 1. And then plus, now my weight is 0.25 times what? 0 this time, because my ANN thinks that it will not be raining, right? The third one is, okay, 0.25 times 1 this time, and then whatever the outcome, 0.75. That means, okay, yes, it will rain today since it's above 0.5, right? This is greater than 0.5. Therefore, my answer will be yes. All right, let's go ahead and do the same thing for this one, right? So basically, we can come in and put their averages here, and then make our process very simple. 0.25, 0.25. So this times this, plus this times this, plus this times this. Basically, my number is sum product, right? Remember, there is a formula that takes the sum product of array 1 and array 2, number by number, and then we can go ahead and that means this sum product multiplies these things one by one and sums them. All right, and our answer is 0.6 again, based on the numbers that we have got here, right? This is the end of the ensembling modeling. Again, the key thing is, okay, we're using the same training, okay, and we're deploying into Rattle, and then out of Rattle, we're making our outcome, okay. CRT thinks differently, ANN thinks differently, SVM thinks differently, and then we want to combine them. If it's a classification, then we apply weighting. If it is a continuous, then we apply, averaging. Sometimes they have equal weights, sometimes they have non-equal weights. If it's equal weights, it's very simple. Go ahead and take the average. If it is non-equal, then we assign the weights, right? And then make our, weighted average for these things, for both the continuous and the classification algorithms, okay? That's it for this video. See you in the next videos.